Okay, let's take a look at this homework. We're looking at theoretical and experimental probability. Theoretical is what? What is theoretical probability? What do you think, Zane? What you think after you do work, you have to base it in math. And so you're usually finding a fraction that you can turn into a decimal or a percent. So theoretical is what you think is going to happen after you look at some statistics or some math. Experimental probability is what? Somebody besides Zane. Somebody besides Ethan. Come on. Some of you have to know what experimental probability is. Excuse me. Cameron told us the other day. So, all right, we're waiting.
All right, it is, wait, you know,
yes, when you try it, when you run some kind of experiment, when you spin a spinner, when you flip a coin, when you roll a dice, when you actually do an experiment, that is the data that you get. So let's look at number 1. A number cube is rolled 24 times. All right, so are we talking about theoretically, or does it look like somebody's running an experiment? What do you think?
experiment.
It looks like it's an experiment. And it lands on 2 4 times, and it lands on 6 3 times. Find the experimental probability of landing on a 2. So we're going back to this experiment. What's the probability that it's going to land on a 2? Well, how many times did it land on a 2? 4 times. 4 times out of what? 4 out of 24. Should I simplify that? Yes. 4 over 24 simplifies to 4 divided by 4 is 1. 24 divided by 4 is 6. 1/6. Find the experimental probability of not landing on a 6. Not landing on a 6. So I need to go back. How many times did we land on a 6? 3 times. So how many times did we not land on a 6? So we rolled 24 times. 21. So 21 over 24. Is that in simplest form? No, those are both divisible by 3, don't you think? So 21 divided by 3 is 7. 24 divided by 3 is 8. Compare the experimental probability you found in Part A, so Part A, to its theoretical probability. So in A, we found 1/6 for experimental. And what do you think the theoretical probability of landing on a 2 is? What is the theoretical probability of landing on a 2? This one's experimental. Theoretical. So if I think about that dice, how many times do you think you would land on a 2 if you rolled it? 1 time. How many sides are there?
6.
And how many sides are a 2?
1.
1/6. So if I were to compare these, it says compare them. What would you say? The probability is the same. The probability is the same. All right. Compare the experimental probability that you found in Part B to its theoretical probability. So in Part B, we found 7/8. And what do you think the theoretical probability is of not landing on a 6? What's the theoretical probability of not landing on a 6? Well, how many numbers on the die are not a 6? There's 5. 5, 6. 5, 6. So, this one was experimental. This one is theoretical. Can I compare those easily? To me, they're hard to tell which one's bigger, if they're close. What could I do to make those to where they're a little more user-friendly instead of fractions? What do you think, Danielle? I'm going to change mine to decimals so that I have a little bit more of an understanding of what I'm trying to compare, because I know this is only 1/8 away from a whole, and this is only a 1/6 away from a whole. So, let's see, 7 divided by 8, and that is, let's round it to the nearest hundred. What is that to the nearest hundred? 88 hundredths. 5 divided by 6, and that is 83 hundredths. So are they close? Are they close? They're close. Are they exactly the same? No. Would that be a comparison? Yes, the probability is close. It's not exactly the same, but it's close. That could be a statement I would make. Okay? I could even say how far apart they are. How far apart are they? 5 hundredths of a percent. They're 5 hundredths of a percent apart. All right. Do you have any questions about what they mean when they say compare now? No? Was that helpful to go over that? Yes. I saw some people just, on number 1, they just circled like A, B, C, or D like it was a multiple choice question. Several people. Just like, it's B. What's B? What? Excuse me? Okay. All right. 2, use the results of the survey in the table shown. A, what is the probability that someone in the survey considered reading books or surfing the internet as the best entertainment value? Write the probability as a fraction. So those are 2 different things. So, it is reading books or surfing the internet. So I'm looking at this one and this one. So, what is the probability that one of those 2 is going to be what they say? So, I feel like I need to add those together. What's 22% plus 9%? If I add those together. So, if I add those together, that's 31%. But it doesn't say to write that as a percent. It says to write it as a fraction. So what did you get as a fraction, Zane?
31 over 100.
31 over 100. Because if I change 31% to a decimal, I change it to 31 hundredths. And 31 hundredths is 31 over 100. And is that in simplest form? Yes, because 31 is what kind of number? If I cannot make it any smaller, it is not divisible by anything other than 1. It is a prime number. All right, so now let's keep going. Out of 500 people surveyed, how many would you expect considered reading books or surfing the internet as the best entertainment value? So, that's the same thing that we're talking about up here. You have 2 different ways. You can use the percent proportion. I could use the 31 over 100 equals how many people out of 500. I could use that. Does that make sense? Or I could say, what is 30, oops, no, that's the right problem. 31% of 500. Do I know how to do that problem? 31%, you use the percent sign. Of means multiplication. Or I can do this. I can say this is times 5. So this is times 5. 31 times 5 is that 155?
Yep.
Or I could have cross multiplied. Or I could actually do the math here. Can I use your calculator, please? And I could say 31. Where's my percent sign?
Oh, you put the second piece and then you put the little parentheses.
Ah, I see it. It's hovering above this left parentheses. 31, second parentheses. So 31% of means to multiply. So that's times 500. And I get 155. Either one of those would have been a sufficient way to solve that problem. So the percent proportion or using your calculator. All right, let's look at C. Out of 300 people surveyed, is it reasonable to expect 30 considered watching television as the best entertainment value? Why or why not? So let's pause here for a minute while you try to figure out, using the information about watching television, is it reasonable that out of 300 people, 30 considered that the best entertainment value? So, I want you to think about how you're going to solve that one based on what we've just done. All right, Zane, what do you think?
3.
3?
Yes.
So the question is it reasonable to expect that 30 considered watching television as the best entertainment value? Why or why not? And you responded
3.
3.
Okay, I got there. How about no?
Yes, how about no? Because the math that you did said, based on this survey, it wouldn't be 30 people that said it, it would be
3.
3 people that said it. So I could say, what is 1% of 300? Or I could say it was 1 over 100 equals how many out of 300? So either way, I should get the number 3.
3.
So 1% of means times 300 equals 3 people. Or 100 times 3 is 300, so 1 times 3 is 3. So the answer is no. And then you would need to reference one of these two problems because, and then you need to have some work to support your answer. All right, any questions on these percent problems right here? Do you see how what we've been doing all year long has been building to understanding these statistics and probability? You don't see that? Have we been doing the percent proportion since about November? And then we're taking it to what we see here? Yes, good. It's good to make connections in math. Okay, 3. A spinner marked with 4 sections, blue, green, yellow, and red, was spun 100 times. The results are shown in the table. So the understanding is, is that it's a fair spinner, meaning that the sizes are all the same, right? Not one's really big and one's really little. The understanding is it's a fair spinner. So we're going to spin it how many times? 100. Find the experimental probability of landing on green. So over here, experimental, I'm going to use this data. So it landed on green how many times? 10 out of how many spins?
100.
10 out of 100. And that simplifies to 1/10. 10 out of 100 is 1/10. Find the experimental probability of landing on red. Wow, these are very different, aren't they?
But then it equals 17 over 25.
So those were both divisible by 4?
Sure.
So you're using your calculator to simplify?
Yep.
Okay.
That's what Mr. Haskins told us to do.
Okay. So 68 divided by 4 is 17. And 100 divided by 4 is 25. So what I expect to happen is if there were 4 of these, I would think they would each theoretically, if we were thinking about what would happen, if we spun 100 times, I would think you would land on each of these how many times? Theoretically, what do you think would happen? There's 4 pieces, and if you spun 100 times, you would think you would land on each one 25 times? Equally. You would think it would happen equally. Theoretically, it should be 25 out of 100 or 1/4. So none of these are really what we would expect to happen. But if you were to continue to run the experiment thousands of times, you would get closer to this 1/4 theoretical probability. So it's always better to run an experiment more times. If the spinner is spun 50 more times, how many of these times would you expect the pointer to land on blue? So we're going to use what really happened. It was 14 out of 100. That simplifies to 7/50ths. And do I even need to do any more math? If I did it 50 more times, how many times would I expect it to land on?
7.
I would expect it to land on it 7 more times. So just simplifying that fraction told me my answer. Did you see how that told me my answer? Okay. All right, any questions on this homework? No?
Can I have the page?
You don't. It's on the back shelf. All right, no questions. Okay, so let's go on to our notes about probability of compound events. So this is before we've been talking about simple events. That's one thing happening. So we're going to move on to talking about more than one thing happening. Probability of compound events. So a new restaurant has opened and they offer lunch. All right, so let's go back. A new restaurant has opened and they offer lunch combos for $5. With the combo meal, you get 1 sandwich, 1 side, and 1 drink. The choices are below. So we're going to look at how many different choices there are for these compound events. There's different events. One event is picking a sandwich. The next event is picking a side order. And the third event is picking a drink. Okay. Have you ever seen that Sonic commercial where they say they have like thousands of choices for different kinds of, is it shakes or slushies?
Yeah, that's a lie.
Something. I think we're going to see how that's not really a lie. Because it's based in math.
Unless they put like 4 flavors in one.
Yeah. So it's because there are different things, so many different things that they can combine that it makes that many different choices. So I think that we're probably going to need a couple of different colors of highlighters. So if you've got a couple of different colors of highlighters, now would be a good time to get those.
Yay, colors.
Alright, so when we make a tree diagram, you always start with listing your choices for the first event first. So our choices for the first event for sandwiches are, you could have a chicken salad sandwich, a turkey sandwich, or a grilled cheese. So you're going to list those first. Chicken salad, turkey, grilled cheese. So you could list them sideways like this. I normally like to list mine like this. I like to work down, but we'll practice it both different ways because you need to be able to read them both different ways. The next thing that happens is, with the chicken salad sandwich, then I could choose chips, french fries, or fruit cup. So off of chicken salad sandwich, I have to draw these brackets that say I could get chips, french fries, or a fruit cup. So how many different choices am I up to on just this one?
3.
3 different choices here. I'm going to get a chicken salad sandwich and either chicken salad sandwich, chips, and then off of that, I can either choose soda or water. So here is one choice, chicken salad sandwich with chips and a soda. That's one choice. All right. My next choice could be chicken salad sandwich with chips and a water. Chicken salad sandwich with chips and a water. So I'm already up to 2 different choices. The next thing I could choose is chicken salad sandwich with french fries or a soda. Chicken salad sandwich with french fries and a soda. Or then I could choose chicken salad sandwich with french fries and water. So I'm up to 4 choices. Next, I could choose chicken salad sandwich with a fruit cup and a soda. Or I could choose chicken salad sandwich with a fruit cup and a water. So just with the chicken salad sandwich, how many choices are there?
2, 4, 6.
6 different choices. Just for that one. Okay?
18 choices.
There are going to be 18 choices. So the next thing is, and you're going to have to know how to make a tree diagram on your own. All right, so then we go to the next kind of sandwich with turkey. With turkey, we could choose chips and a soda, or we could choose turkey, chips, and water. So now we're up to 8. Then I could choose turkey, french fries, and soda, or I can choose turkey, french fries, and water. The last thing is, let's see, let's choose a different color. Turkey, fruit cup, and soda. Or turkey, fruit cup, and water. So now I'm up to 12 choices. And the last thing now, if I want a grilled cheese, I could do grilled cheese, chips, soda. Or grilled cheese, chips, and water. I'm up to 14. Now I could do grilled cheese, french fries, and soda. Grilled cheese, french fries, and water. Or grilled cheese, fruit cup, soda. Grilled cheese, fruit cup, and water. There are 18 total combinations. All right, so there's some math that we can do to get there so that we don't always have to do a tree diagram, but you'll see how the tree diagram is helpful in just a minute. So there are 18 total combinations. Here, the math says there are 3 choices for sandwiches, 3 choices for sides, 2 choices for drinks. If you multiply 3 times 3, you get 6. No, 3 times 3 you get 9, and 9 times 2 is 18. So if you multiply these choices together, 3 times 3 times 2, you get 18 choices. So if it just wanted to know what the choices are, you can use math and just multiply the number of each choice times all the choices. You're going to find out how many there are. But sometimes you need to have what's called a sample space. You need to have a sample space, and that's where you're going to list all your combinations. So we're going to use abbreviations. For chicken salad, we're going to use a C. For turkey, we're going to use a T. For grilled cheese, we're going to use a G. And then we'll use the C for chips, F for French fries, and A for fruit cup. So we're going to list our choices. Our first one is we're going to say CCS. CCS. Next, we're going to say CCW. CCW. That's these first two.